Good afternoon. My name is Nehal Abdelwahab. I'm a PhD scholar in East Carolina University, and the presentation of the work I'm going to present to you today is under the title of Systematic Study for Recycling Iron Oxides Bearing Sintering Residuals for Hard and Soft Ferrimagnetic Glass Ceramics Preparation. And I did this work in my home university in Mini University in Egypt. The outline. Firstly, I'm gonna tell you the goal of my work, and after that, a brief introduction, the methods, results, and characterization, conclusions, and future work. Sintering process is a pre-treatment process for the iron ore. For the iron ore and steel industry. In this process, the small particles are agglomerated to form larger particles to be a burden in the blast furnace. In this process, the fine iron ore particles and secondary iron ore oxides our combustion, a combustion is happened to the fine iron ore particles and secondary iron oxide wastes in the presence of lime and coke to produce a molten mass. This molten mass is solidified after that to porous pieces, which are crushed to a smaller particle sizes. Those particle sizes are divided into three categories. The particle sizes larger than 20 millimeters are supposed to be a burden to the blast furnace, and from 5 to 20 millimeters can be reintroduced in the center machine, and less than 5 millimeters are considered as a waste. So the idea is to have those amount of particle sizes which is lower than 5 millimeters and to prepare a magnetic glass ceramics. Actually, those amounts are represent 25% of the sintering process, so it's a very large amount. The question is why it is important to convert those sintering residuals into a ferrimagnetic glass ceramics. Actually, the world's expenses of magnets are $8 billion annually. And the global consumption of all types of magnets is over 500,000 tons per year. And most raw materials, especially steel and cobalt, became rapidly increasing in price. It reached 100% just the last year. So it's very expensive. And this graph represents that the world consumption of ceramic raw materials for magnets preparation, and it reached 60%. So from all of that, we can say that we can know how it is very important to prepare soft and hard magnets from just waste, from waste recycling, which costs nothing. The hard and soft ferrites are very important because they have wide range of applications, and for example, in hyperthermia treatment of cancer, gas sensors, catalysis, magnetocaloric refrigeration, drug delivery, ferrofluid technology, information storage systems, transformers, and tissue engineering. And in tissue engineering actually is what we are doing in Dr. Barbara Muller's laboratory here in East Carolina University. The method of the preparation. Actually, we add some additives to the sintering waste. Sorry, it's sintering waste, not RSW. It's just SW. It's wrong. We add some additives to the sintering waste and put them in platinum crucible. Where we put it in a furnace. The hard ferrites melted at 1,200 degrees Celsius and soft ferrites at 1,400 degrees Celsius. Occasional swirling during the melting process is very important to ensure the homogeneity. After that, pouring on a steel plate. Bracing by another blade for thin strips, and after that, those are the final magnetic glass ceramics. The results and characterization. Firstly, we wanted to see, to look what is the chemical composition of those iron centering wastes. We should know the composition of this material firstly. So from the XRF result, we see here that it contains a high level of iron oxide and traces of other inorganic oxides. And this is the chemical composition of the magnetic glass ceramics we prepared. Firstly, we prepared a reference soft and reference hard samples from pure chemicals to compare with the soft and hard ferromagnetic glass ceramics we prepared. And here, as we see that the reference soft and soft ferromagnetic glass ceramics and the reference hard and hard magnetic glass ceramics have nearly the same elemental composition, except that the prepared soft and hard ferromagnetic glass ceramics contain extra oxides. Those extra oxides will enhance the properties of the material we prepared, as we will see after that from the characterization. The main constituents of the soft ferrites are iron oxide and zinc oxide, and the main constituents of the hard ferrites are iron oxide and barium oxide. We wanted to examine the thermal properties of our prepared material, so we did the DTA. And as we see here, that the TG of the soft magnetic glass ceramic is less than the reference soft sample, and this is an indication of how the extra oxides enhanced the properties of the prepared soft magnetic glass ceramics. It reduced the TG. And here, this exotherm at 830 is an indication for the zinc ferrite presence, for the zinc ferrite phase presence. And here in the hard ferrites, we can see that, in contrary, the TG didn't reduce here in the hard magnetic glass ceramic. And this is maybe because we can see two endothermic peaks before the TG at 46 and 116 degrees Celsius. And this can be, and this is due to the additional oxides added to the hard magnetic glass ceramic. And this can be a pre-crystallization and pre-organization for the atoms before the TG. Also here, the peak here in the hard magnetic glass ceramic at 803 is an indication for the barium hexaferrite presence. And in the hard magnetic glass, in the reference hard, those peaks also are an indication for the presence of the barium hexaferrite, which is the magnetic phase. After the DTA, we choose 900 degrees Celsius per 2 hours to be our heat treatment schedule. We wanted to examine the phases and the formed phases of our material, so we did the XRD, the X-ray diffraction analysis, and here we can see that the centering waste contain both zinc ferrite and hematite phases, and the soft magnetic glass ceramic contains just the zinc ferrite, and after heat treatment, some of the zinc ferrite transformed to hematite. So we can say here clearly that the heat treatment reduced the zinc ferrite crystallization. And here in the hard ferrites, we can see that all the zinc ferrite and hematite converted to barium hexaferrite in the hard magnetic glass ceramic. And after heat treatment, the amount of barium hexaferrite crystallized increased very much. So we can say clearly also that the heat treatment enhanced the barium hexaferrite crystallization here, which is also the magnetic phase, the desired magnetic phase. We wanted to to see the morphology of our particles and to examine the particle size, the particle size and particle size range. So we did the TEM, and here we can see that in the soft magnetic glass ceramic, zinc ferrite with particle size range of 22 to 62 nanometers, and after heat treatment, some hematite appeared with particle size range of from 5 to 8 nanometers. And in hard magnetic glass ceramic, we have barium hexaferrite with particle size range from 9 to 13 nanometers. And after heat treatment, the barium hexaferrite also present with particle size range from 2 to 12 nanometers. This is the most important analysis we did because we wanted to examine the magnetic properties of our material. So we did the vibrating sample magnetometer test. And here we can notice that the saturation magnetization increased from the centering waste to the soft magnetic glass ceramic, but after heat treatment, the saturation magnetization decreased. And we can relate this with the results of the XRD, as after heat treatment, the amount of zinc ferrite, which is the magnetic phase, the amount of zinc ferrite after heat treatment decreased. That's why the saturation magnetization decreased as well after the heat treatment. And here the VSM for the hard ferrites. We can see here that the saturation magnetization decreased from the centering waste to the hard magnetic glass ceramic, and after heat treatment it enhanced. So we can say here that the heat treatment enhanced magnetization and coercivity as well, of course. And this also is related to the amount of barium hexaferrite crystallized. After heat treatment, the amount of barium hexaferrite increased. That's why the saturation magnetization increased after heat treatment. It's related. We can conclude that with our method, we were able to use the iron oxides wastes from centering plants to prepare ferromagnetic glass ceramics that have a great applications. Differential thermal analysis revealed one broad exothermic peak for the hard magnetic glass ceramic had one broad exothermic peak also, and those are related to the zinc ferrite and barium hexaferrite for soft and hard magnetic glass ceramics. The X-ray diffraction analysis shows crystallization of hematite and zinc ferrite phases in the centering waste, and zinc ferrite and barium hexaferrite in soft magnetic glass ceramic and hard magnetic glass ceramic. So we succeeded to prepare our magnetic phases, which are zinc ferrite and barium hexaferrite in soft and hard magnets. And the particle size range from the TEM is the nano-sized particle is more than 20 nanometers for the soft magnetic glass ceramic, and less than 15 nanometers for the hard magnetic glass ceramic. So we are still in the nano range, which is supposed to be from 1 to 100. The vibrating scanning magnetometer, which is the VSM, revealed increasing saturation magnetization from for the centering waste to the soft magnetic glass ceramic, and decreased after that, and it decreased from the centering waste to hard magnetic glass ceramic. And number 6, the heat treatment decreased magnetization in soft ferrites and enhanced magnetization in hard ferrites. I'd like to thank my mentors in Egypt and here in East Carolina University. And thank you for you all. Any questions? No questions. Excuse me? The type of magnetism? Yeah, it's not super. Excuse me, I didn't hear you. coolest behavior. Yeah, it's supposed to. I didn't. No, I didn't change the temperature. It is just on. I think it was at 300 Kelvin. I think so, but I didn't change the temperature. But it's supposed to be very different. If we tested in different temperature, but we didn't do. Just this is just on 300 Kelvin. This is your question, right?
Anybody else? Okay, thank you very much.
Thank you.